Hello, my name is Kayla De Leon,
And my name is Janelle Soto.
and today we'll be talking about the human eye.
The eye has three layers: the fibrillary layer, the vasculus layer, and the inner layer. The fibrillary layer contains the sclera, which is the white of the eye, and the cornea. The vasculus layer contains the choroid and the vitreous humor, which is a jelly-like substance inside the chamber of the eye. The inner layer consists of the retina, which is where we have cones and rods, which help us process what we see. They're tied to ganglion cells, which are receptors in the eyes. Rods help us see black and white colors and detect movement, while cones help us see colors and detail. Staring at colors too long can tire out your eye, your corneas and rods. This leads to an after image where the colors are opposites for the cones and negatives for the rods.
And this.
Staring at it for about 15 to 30 seconds will create a negative image for the rods. While this, staring at it for 15 to 30 seconds, will create a opposite image of the colors for the cones.
Eyes are like cameras. The cornea would be like the lens. Here, most of the light that enters the eye is focused. The iris controls the amount of light that makes it to the back of the eye. It increases and decreases similar to a diaphragm. The eye crystalline lens works like an autofocus lens. It helps the eyes focus on near and approaching objects through a process called accommodation. The light that has been focused by the cornea and crystalline lens and limited by the iris and pupil then reaches the back of the eye. The retina, the back of the eye acts like the image sensor in the camera, which turns image into electric signals. They're then sent to the visual cortex, which controls our sight. Here's the formula to calculate where the focal point of the image in the eye is to help us understand how we see things and how defects in the eye affect it. So here is 1 over f equals I over the distance, 1 over the distance of the object plus 1 over the distance of the image.
There are three factors that affect the eye's refractive abilities: the length of the eye, the curvature of the cornea, and the curvature of the lens. The most common problems for the eyes are nearsightedness, which is also known as myopia, farsightedness, which is known as hyperopia, and astigmatism, which is a defect of the eye where it's shaped in a non-spherical way. Nearsightedness happens when the eye is too long that the light is focused before it can reach the retina. In order to correct this, a concave lens is used to make sure it gets focused as it hits the retina. Farsightedness or hyperopia, it happens when the eye is too short that it doesn't get focused before it reaches it, so it gets focused in the back. In order to correct this, we use a convex lens so that it's focused right as it reaches the retina. When the cornea is not in a perfect sphere, it's called astigmatism. This causes the optical image to be refracted or irregular focus, so that there's various focal points instead of just one. In order to correct this, we use an uneven lens so that all focal points are at the retina. A person can be both nearsighted or farsighted with or without astigmatism. In order to correct that, we would use bifocal lenses, which have both concave and convex lenses, so that people can see both far and near. The eye has a near point of 25 centimeters, which is the closest it can see without it becoming blurry. It has a far point of infinity. Using the focal length formula, 1 over f equals 1 over distance of object plus 1 over distance of image. We'll be solving for near and far away object focal length. So let's say we have a small object, such as a button, and it's near the eye, about 26 centimeters. And the distance of the eye would be around 2 centimeters. So plugging that into the formula, 1 over 26 centimeters plus 1 over 2 centimeters, we get an answer of 0.538. We inverse it to get the focal length of 1.6 diopters. For a faraway object, let's say a tree, if it's 25 feet away or 762 centimeters, and the distance of the image distance is once again 2 centimeters, we plug that in to get 1 over 762 centimeters plus 1 over 2 centimeters, and we get 0.501. We inverse that to get the focal length of 1.99 diopters.
So here we are going to be finding the final image of this problem, and this problem is find the location and total magnification of the final image produced by the lens system shown below if the positions of the two lenses are reversed. So here is the image produced by lens 1, it's the object for lens 2, and here will be the image produced by lens 2, and it's the final image of the system. So here is a concave lens, and the second is a convex lens. Lens 1 produces a reduced upright image to its left. The image is the object for lens 2. The final image of the system produced by lens 2 is tiny and inverted. The thin lens equation can be used to find both images of this in the system. What is known is the focal length of lens 1 is negative 12.5 centimeters. The object distance for lens 1 is 20 centimeters. The separation between lenses is 50 centimeters, and the focal length of lens 2 is 10 centimeters. So what we are trying to find is the location of the final image and the total magnification. So using the thin lens equation, we're able to find the image distance for concave lens 1. So we already had the object distance for image 1, and that was 20 centimeters. And we also had the focal length of concave 1, and that was negative 12.5 centimeters. So putting it into the equation and putting it into the calculator, you get negative 0.13, and once you solve it, you get negative 7.69 centimeters, which is the image distance for concave lens 1. So then you're going to add the image distance from the concave lens 1 to the separation between lenses, which is 50 centimeters, in order to get the object distance for convex lens 2, and that will give you 57.7 centimeters. In order to find the location of the final image, we're going to use the object distance and the thin lens equation to find that. So the object distance for lens 2 is 57.7 centimeters. We don't know the image distance for lens 2 yet, but our focal length for lens 2 is 10.0 centimeters. Putting it into the equation, we we get 0.0826, and then once you put it into the calculator like this, we end up getting 12.1 centimeters for the image distance from lens 2. So if the positions of the two lenses are reversed, it's kind of like the different result you would get when you look through the wrong end of a pair of binoculars. And you can see that from the total magnification of this problem. And by finding that, you first go by lens 1, and you're going to do image distance divided by object distance. So here you will have the negative 7.69 divided by 20, and that will give you 0.385. And the magnification by lens 2, you're going to be dividing the image distance from lens 2 by the object distance by lens 2, and that's negative 12.1 divided by 57.7 centimeters, and that will give you negative 0.210. And you're going to multiply those two magnifications, and that will give you negative 0.0809. And this is the final image, and it is reduced by this factor, and it is inverted.